So, having derived the backpropagation algorithm from first principles for a single layer of hidden neurons, let us summarize the computational steps and then provide an outline of the algorithm. Okay. So, if we were to formalize the details of the backpropagation algorithm computational steps that we discussed thus far, we have two passes. The first is the forward pass, the second is the backward pass, right. And if you have to think how this computation happens in the forward pass, basically from one node to the other node you have all the functional signals that are scaled by the synaptic weights, and this is how the computation works. But in the backward pass, from the output neurons you basically have the error signals, or I would say the local gradients of the errors that will get propagated, scaled by the synaptic weights times the derivative of the activation function. This is how it is going to proceed, right. So, clearly if you think about in terms of the signal flow graph, in the forward pass you have this kind of computation where you have all the function signals that you compute, and the backward pass you compute the local gradients towards the synaptic adaptation. So, this picture has to be very clear, right. So, I will just write it up for the purposes of clarity. Here it is all the function signals, and here we will deal with the local error gradients that eventually would lead to synaptic adaptation. Okay. Now, let us summarize the steps of the forward pass. So, in the forward pass, the synaptic weights remain unaltered through the network, because we are not doing synaptic adaptation here. So, we fix the weights as a consequence of what synaptic adaptation was done during the previous computational step of the backward pass. Okay. So, the weights are fixed in the forward pass. We are interested in computing the function signals at each and every node within a layer. Okay. Suppose you have layer L, then the function signal y suffix j at layer L at time step n is computed as the nonlinear activation function of the local reception field that this node j sees, and the local reception field at neuron j time instant n in this layer L is given by this quantity, which is basically the summation from I equals 0 to L minus 1 w j I at L minus 1 times y I at L minus 1. So, this is the local reception field, at layer L at node j in the Lth layer. This is basically summation I equals 0 to L minus 1, the synaptic weight connecting neuron j with neuron I in the previous layer times the function signal in the previous layer. And that previous layer, just observe this, the superscript, right, observe the superscript. Now, if the neuron J is in the hidden layer, if neuron J is in the hidden layer, then we can say the function signal yi of n in layer 0 is basically the input xi, right, for all I equals 1 to m naught except the bias when I becomes 0. When I becomes 0, that is the subscript I becomes 0, it is the 0th coordinate, which is basically the bias. So, the forward pass is very straightforward, but when you are coding up, right, you have to pay particular attention to the weights, because the weights that you have in the forward pass is a result of the weights that you had as a result of the synaptic adaptation in the backward pass of the previous computational step. Now, the backward pass is pretty straightforward. It starts at the output layer by passing the error signals backwards through the network, layer by layer, by computing the local gradients recursively. This is very, very important. So, if you have gotten a feel for how the local gradients are computed for a neuron in the output layer and for a neuron in the hidden layer from the signal flow graph, I think you are sort of ready to sort of summarize the steps in the backward pass. So, how do we do this for different kinds of activation functions, right? This is an important step, because so far we just assumed some phi to be the activation function, we never defined what phi is. Now, let us discuss specifically for these cases. Activation functions are in general nonlinear functions, they have nonlinearities, but since we are taking the derivative, it must be differentiable, which implies that it must be continuous. You can also force some rule to compute the derivative. For example, you may treat an activation function, it may not be a nice smooth function. If you think about a smooth function, that means it has some orders of derivatives that you can take, first order, second order, third order, so on. It is k smooth, you can take those k derivatives, right. But here we are only concerned with the first derivative, because we deal with the gradient descent, which is basically based on just the gradient, which is the first derivative. So, therefore, at one pass if we are able to differentiate, we are home for good. But there may be functions such as this, which is the Heaviside function. This is also sort of a nonlinear function, but this has a discontinuity at the origin, right. So, these are all possibilities, and we can define some derivatives at points where things are not continuous, and then we can proceed. But let us discuss some basic activation functions, and we will discuss with these other cases such as the sine function, etc., when we discuss some of the pathological cases associated with these activation functions, and then how this can be done towards deep networks. Now, coming back, the logistic function is given by this equation phi of Vj n, that is always the activation function works over a local reception field. So, the term local reception field is more a qualitative term, but when you put this quantity Vj of L of n, then you are bringing some quantitative aspects to that. That means that is the quantity or the variable at neuron j in the Lth layer and time instant n. Okay. So, this is given by this quantity 1 upon 1 plus exponential minus a times Vj of n. This is the function, and a is an adjustable quantity, and typically we assume a to be greater than 0. Now, you can take the derivative, which is straightforward from your calculus. You have 1 over 1 plus exponential something. So, take the derivative, it is minus 1 upon 1 plus exponential square times the derivative of 1 plus exponential something. this 1 is a constant. So, therefore, you take the derivative of this exponential. So, it is minus a times exponential of minus a times I mean a times exponential minus a times Vj of n, right. This is what we have here, right. This is straightforward. So, phi dash is basically a times exponential of something upon 1 plus exponential of something, where something is minus a times the local reception field at the neuron j in the lth layer, and this holds for layer 1 and layer 2, right, because we are considering still a single layer. But this is not restrictive to just a single layer, we can do it for any lth layer. Now, Yj of n is basically phi of Vj, and if you do a straightforward algebra, phi dash of the local reception field is a times Yj times 1 minus Yj. So, if you know the function signals at node j for the lth layer, then you can compute the derivative of the local reception field in terms of just the functional signals Yjn in the lth layer scaled by this constant a, right. I mean a times Yjn minus a times Yjn times 1 minus Yjn. So, I repeat again, it is a times Yjn times 1 minus Yjn, that this holds for L equals 1 comma 2. Just observe this equation. Now, for a neuron j located in the output layer, Yj is basically Oj in terms of our notation, O standing for the output. If you are not comfortable writing it as O, you can ignore, you can just treat this as Yj n as long as you indicate the layer number appropriately. Now, the local gradient delta j for the output layer, which is 2, is given by Ejn times the derivative of the activation function of the local reception field at evaluated the local reception field for neuron j in the output layer, right. And all these things are for a particular time instant n, because we do not have any self feedback or any recursion involving a different time step. So, therefore, it is all at time step n. Now, Ej can be realized as Dj minus Oj, right. Ej of n is Dj of n minus Oj of n, and I have deliberately removed the superscript 2 here because it is sort of direct and implied that this is a measurement in the output layer, right. We get this. Now, going by this term here, phi dash, the derivative of the activation function. So, this term we just plug in, I call this equation 1. So, I just plug in 1 into this computation for the derivative of the local activation field, and that is given by A times this Yj is replaced by Oj because it is defined like that, right. So, A times Oj times 1 minus Oj, all at time instance small n, right. So, this is pretty straightforward for us to compute. Now, for an arbitrary hidden node j, we can compute the local gradient delta j, right, and this is given by the derivative of the activation function evaluated at the local reception field seen at the neuron j in the lth layer times this summation over all these scaled local gradients from the output layer, right. The scaling is through the synaptic weights Wkj that connect the output neurons k with this hidden node j, right. This is sort of straightforward. So, just again pay attention to the signal flow graph as you do the computation, so that the layer numbers are all clear when you do the computations. But all we have to care about is the derivative of the activation function, because that is what we are concerned at this stage. So, for the logistic function, the derivative of the activation function is given by this quantity, it is a times yj n times 1 minus yj n at layer 1. So, you just plug this straightforwardly and then you can compute the local gradient in the hidden layer, right. So, as a part of homework exercise, I would like you to sketch this activation function. So, I gave you this equation here couple of slides back. I want you to sketch this function phi, this logistic function, how it looks as a function of the local reception field and this constant a. Pick some constant a which is greater than 0 and then plot this function. Take the derivative of this function, plot this function, and can you investigate if you can see a maximum for the derivative. I just want you to try this exercise as a part of your homework. Another activation function one can think of is the hyperbolic tangent function. Most of you might have seen the tan hyperbolic function as a part of your calculus exercises, right. You would have taken derivatives of tan h or cos h or sin h and all these type of hyperbolic functions, but you would realize that this function that you routinely took it for granted has applications within neural networks, that is a tan hyperbolic function. Now, the tan hyperbolic function, the activation function for the tan hyperbolic function is given by a tan h b times bj of n. So, just recall tan h is cos sin h upon cos h, and you can expand sin h and cos h and you can compute in terms of these exponentials. I think this is sort of straightforward. Now, the derivative of the activation function is given by a times b. So, in the arguments of the tan hyperbolic we have b to be a quantity which is greater than 0, and the coefficient of tan hyperbolic is a quantity a which is also greater than 0. So, derivative of tan h is secant h, secant hyperbolic square, right, and if you do the simplifications we get a times b times secant hyperbolic square of b times the activation local reception field, right, b times the local reception field at node j. You use the identity secant h square is 1 minus tan h square, and now it is a square minus b. You have this identity form which is x square minus y square is x plus y times x minus y, and expand this out and then pull this a square and then you do the simplification, and this is straightforward. I will avoid the steps. So, you can easily do this. You can take it 1 minus tan h times 1 plus tan h, then you have this b that is sticking out here, you multiply by a square, you have an a here, right. What I will do is I will pull an a here, I'll multiply this by a throughout, I'll have a, another a here, right. So I will multiply and divide by a, that is what I did. So one of these a's I pulled in into one of these terms here and I multiply and divide by a, and this a tan h is basically what I have as my yj, right. So this is straightforward algebra, and I think you can do this yourself and verify that this result is valid. So this holds for layers 1 and 2. Okay. Now for a neuron j in the output layer, you can compute the local gradient delta j. So what we have to do is we have to calculate the local gradients for neurons in the output layer as well as in the hidden layer for this activation function, which is basically the tan hyperbolic. So therefore we have to do this straightforward math. So delta j for the output neuron is given by this equation, Ej times the derivative of the activation. Do the straightforward derivative of the activation function using the formula that I wrote earlier. So using that you can simplify using this equation that you have here, okay, which is b upon a times dj minus oj times a minus oj times a plus oj, where oj is your output response, that is the response, the function signal in the output layer for node j. Okay, now it is again straightforward for the hidden layer node. Since you have done the logistic, we can extend this straightforwardly for the tan hyperbolic, except that replace the derivative of the activation function evaluated at the local reception field using the formula b upon a times a minus yj times a plus yj. That is all, it is pretty straightforward. The rest you can compute recursively, because delta j you already did this for the output layer. You have to plug that in here and then evaluate it for what you would get for the local gradients in the hidden layer. Okay. Now all these steps are sort of straightforward and clear, because now if you want to compute delta j in layer 1, you need to compute delta k in layer 2. You see how there is dependency across layers, right. If you cannot compute or if you do not have the handle to the local gradient for a node in the output layer, you cannot compute the local gradient for a node in the hidden layers. So that is the first step. So therefore you have to sequentially proceed layer by layer all the way from the output layer to the hidden layer, the first hidden layer. Okay. And another important observation which is directly coming as a result of the concept is as follows. In the case of the neuron in the output layer, the error is visible to you, it is directly available, this is directly available. But in the case of the neuron in the hidden layer, the error is not directly available, and that is the reason you have to compute using the local gradients that you computed for nodes in the output layer. Okay, and pay attention to these superscripts carefully. otherwise you would make errors when you have to run your code. So, having discussed how to compute the derivative of the activation, having discussed the activation functions and how to compute the derivatives of the activation function, let us proceed towards understanding how the learning rate can influence the dynamics of the backpropagation algorithm. This is very important. So, eta controls how the synaptic weights have to be adjusted proportional to the derivative of the total instantaneous error energy that you see at the output. Okay. Now, the BPA provides an approximation to the trajectory in the weight space through gradient descent. Now, let us imagine this bowl that we have here, right. This is the surface, this is the performance surface, this is like a bowl. Now, the smaller the value of eta, the smaller steps that you take. So, I will indicate it possibly in green. You take small steps like this. If eta is small, you go through small steps to reach the bottom of the bowl, and the trajectory is also smooth because you are taking baby steps, but you have a slower rate of learning. That is the consequence of this, that is choosing a smaller value of eta. But what happens if we choose large values of eta? If you have too large an eta, there can be oscillations because you can bounce from one side of this wall to the other side of the wall, and then you can rattle like this back and forth till you reach the optimal point. This can be sort of visualized or rather understood if we imagine a marble that is sliding through a bowl, right. Imagine a dish bowl that we have, the fruit bowl, and we are sliding a marble through it. So, if you let the marble, let us say there is some amount of friction on this dish bowl, and it does not just go and settle down at the bottom of the bowl, but if you give a little bit of push, you can let the marble slowly go down and settle at the bottom. But if you give a large push, you shoot this marble, it may not slide along this wall, but it may go on the other side of the wall and then rattle back and forth and finally rest at the bottom, right. And that is sort of how one can visualize the dynamics of the learning rate on this algorithm. So, one has to be very careful to adjust the learning rate in such a way that you can control the speed of convergence, at the same time avoid these oscillations, because if you are oscillating a lot, then you are losing time towards convergence. So, rather take optimal steps and reach the bottom of the bowl. Okay. There are also Hessian based techniques that you can use towards optimization, and we will discuss this subsequently in more advanced classes. Now, the learning process does not stop just by adjusting the learning rate. There is also something called the momentum term that we can introduce to sort of give a push to the learning rate as a consequence of how the synaptic weight was, or how our adjustment was at a previous time instant. So, this is given by this equation. delta wji of n is alpha times delta wji of n minus 1. Just think about the connections with the time steps. Right. The synaptic adaptation, the delta synaptic adaptation at time instant n is alpha times the delta synaptic weight at n minus 1 plus eta times your local gradient times the input. So, this is error times input standard gradient descent, right. This is a standard term through gradient descent. So, that we got as a function of eta delta j and yi, plus we can control the rate of this decay, that is if we want wji to accelerate fast, we can control this rate of decay alpha, we can make alpha close to 1, we can make it large, or we can let alpha to be very small, then the influence of delta wji at a previous time step would be very small, right. So, alpha sort of controls the rate of decay. Now, one can imagine the signal flow graph for the momentum update using this diagram that I have here. So, this is the adaptation at time step n, that is delta that I have to apply to the previous weight. The delta is going to be some alpha times the delta that I had at time step n minus 1 plus the local gradient and the function signal I have instantaneously at that time step, right. This is basically a first order autoregressive process in terms of the weights, but it is you can say this is time varying because depending upon the adaptation, because of the examples that you see, you will have your synaptic weights adapt to these examples, that is to your feature vectors. So, this is like a first order autoregressive process because you have this feedback. Now, you expand this out, which is straightforward based on the recursion equation that we have here. So, I will call this, use a different color here. Recursive equation, let me call capital A. So, expand this recursive equation and I get this form here, which is eta times summation. I will introduce this variable t equals 0 to small n alpha power n minus t times delta j of t times yi of t, right. And you can interpret delta j times yi to be the negative gradient of the error with respect to the synaptic weight, and you have this eta, which is basically what you have here, and this alpha now regresses itself in powers of a decaying exponential, right. These are powers of a decaying exponential, right. When n minus t is 0, it is 1, and if n minus t is large, then it basically is close to 0, right, because and this sort of controls how much of influence delta j and yi will have a bearing on the synaptic weight at time instant n. Okay. So, this is sort of straightforward. Now, there are a few observations. So, delta wj at time step n is minus eta times summation t equals 0 to small n alpha power n minus t times the partial derivative of the error with respect to the synaptic weight Wji. Now, current adjustments comprise of a sum of exponentially weighted time series, right. So, this is what we have, and we can restrict alpha to be between 0 and 1. So, there are two things: when this derivative has the same algebraic sign, that is derivative of E of t with respect to Wji can have the same sign, or it can have a different sign over consecutive iterations. So, if this partial derivative of E of t with respect to Wji has the same algebraic sign over consecutive iterations, then Wji grows in magnitude, which is obvious, and adjustments on the weights happen on a large scale, that is you are accumulating mass because of this sum, because you are adding them up, because they have the same algebraic sign. So, this implies we have an accelerated downhill, that is we are going down pretty fast. If however we are having opposite signs over consecutive iterations, then Wji shrinks in magnitude and it has a sort of stabilizing effect, that you are accumulating some mass, then you are removing some mass, and you basically rattle, and finally you have a sort of stable effect. So, you can control the learning rate, and that has a bearing on how the dynamics of the algorithm can be, right. It depends upon the instantaneous gradient that you compute. We do not know how the sign is, when you compute day by E by day by Wji or consecutive iterations, you do not know how the sign would be. If it is the same sign, you are accumulating mass. If it is opposite signs, you are having a stabilizing effect, because you do not grow that quantity, right, you are sort of balanced. So, controlling eta as a result of how the gradient works, you can control the dynamics of the algorithm, but at this stage you can be pondering that why should I keep eta to be fixed. This is a nonlinear dynamical system. Controlling eta can control the dynamics of the algorithm. So, we can have varying learning rates, and if we have varying learning rates, then the dynamics of the algorithm becomes complicated, and analysis of the algorithm towards finding out the right parameters to get the system stable, that would be pretty hard, because you will have to do a sort of a local stability analysis and then figure out the eigenmodes, etc. This would be very hard if we let the learning rates adaptable or adjustable. But if you let it adjustable, then you have a better control. You can, if you can control carefully, then you can have accelerated dynamics, and this is one area where one can kind of bring in heuristics or some analytical rigor to figure out how to set the learning rates optimally. Okay. So, that is why I mentioned here the pros would be more flexibility, which means better approximation, and the cons would be difficult to control because of nonlinear dynamics. Okay. So, with this we will stop here. So, we have understood the role of learning rate and how one can control the dynamics of the algorithm, and through the subsequent lectures concerning BPA we will study the XOR problem, and then we will go into the details how we can sort of solve a pattern classification problem which is essentially not linearly separable using the hidden network with an appropriate choice of activation functions. We will stop here.